Hi, my name is Yashica, and I'm proud to introduce our group for the 2025 NASA Seas Open Cluster team. Abdullah, Cindy, Rodrigo, Lewis, Ashwin, and I worked hard over the past few weeks to present our work to you. Before we dive in, let's start with what an open cluster actually is. Open clusters are groups of a few dozen to a few thousand stars that all form together from the same giant molecular cloud. They're loosely bound by gravity, so unlike the tightly packed globular clusters, open clusters are more spread out, and over time they can even drift apart. You'll usually find them in the disk of a galaxy, especially in the spiral arms where new stars are born. Since they form from the same material, the stars in an open cluster have similar ages and chemical makeups. Some examples include the Seven Sisters and the Hyades, both found in the constellation Taurus. So how do open clusters actually form, and what happens to them over time? It all starts in a giant molecular cloud, a huge region of gas and dust. Parts of that cloud collapse under gravity. Stars are born, often in loose groups ranging from a few dozen to thousands. The massive stars have intense stellar winds, and that blows away any leftover gas, shaping what becomes the young cluster. Once that leftover material is cleared out, the cluster stabilizes a bit. The stars are still loosely bound by gravity, but now they settled into a recognizable group. Since they've all formed from the same material at the same time, they share a common age and composition, though each one evolves differently depending on its mass. But open clusters don't last forever. Over time, gravity from passing clouds, other stars, and even the galaxy itself start tugging on them. Eventually, the cluster slowly dissolves with the stars scattering into the galaxy. So, the structure of an open cluster, they're essentially a loosely bound group of stars spanning a few light years with an irregular or spherical shape. Since they have weak gravitational binding, they're prone to dispersal. Open clusters are composed of very metal-rich stars, and they often include massive blue stars. So, why do open clusters matter? Why should we study them at all? First off, they're perfect for studying how a star's mass affects its life. Since all stars in a cluster are the same age, any differences in how they evolve come down to mass, making comparisons super clean. They also help us fine-tune how we estimate stellar ages in general. If we can age a cluster accurately, we can use that to calibrate models for other stars. The star's chemical makeup gives us a snapshot of what the interstellar medium was like when and where they were formed. And because they tend to live in the spiral arms of galaxies, mapping where open clusters are helps us trace the structure and evolution of the Milky Way itself. Lastly, over time, heavier stars tend to drift towards the center of a cluster. That tells us a lot about gravitational interactions and how these systems behave internally as they age. This brings us to our project's problem and goal. The problem is that we have lack of precise data on the physical properties of stars within a distant open cluster around 10,000 light-years away. This is so important because this limits our ability to accurately determine the cluster's age and distance. And open clusters are so important because they can help improve models of how stars evolve and measure distances in the galaxy. This brings us to our goal, to determine the age and distance of an open star cluster located 10,000 light-years away.
Our data was collected using a telescope from the Southeastern Association for Research in Astronomy, or SARA Consortium, and particularly their telescope in Cerro Tololo, Chile. This telescope has a 0.6 meter aperture or diameter, and is unique from the other SARA telescopes in that there is full access to the entire southern hemisphere sky from its location. The telescope is a reflecting telescope, meaning that it uses mirrors to gather and focus light into the CCD detector. Our data was collected using a telescope from the Southeastern Association for Research in Astronomy, or SARA Consortium, and particularly their telescope in Cerro Tololo, Chile. This telescope has a 0.6 meter aperture or diameter, and is unique from the other SARA telescopes in that there is full access to the entire southern hemisphere sky from its location. The telescope is a reflecting telescope, meaning that it uses mirrors to gather and focus light into the CCD detector. This gives it some unique advantages, but also challenges compared to other telescopes. The reflecting telescope used to collect our data will exhibit no chromatic aberration, meaning different colors are not refracted differently, and improving image quality. Reflecting telescopes are also easier and cheaper to scale compared to other types of telescopes. They can observe fainter objects, which is important in our case for picking up on faint stars in the open cluster, more readily than refracting telescopes could. However, there are also some unique challenges that come with ground-based telescopes in general, and also the one that we are using. First, ground-based telescopes face atmospheric interference, or SIA, which is when air movements or different particles in the atmosphere distort incoming light, leading to lower resolution or blurred images. Additionally, the inside of the telescope must also be kept at a similar temperature to the outside air. Temperature heats and cools different parts of the telescope differently. The edges might cool faster than the middle, which affects how sharp the focus is and where the focus is. Throughout the night, the temperature change can mean where the telescope is focusing changes, and there may be drift in the observation. Finally, interstellar medium, the gas and dust between stars, can obstruct our ability to see distant and faint objects. To analyze our data, the images were processed in 3 different astronomical filters. These filters block the color spectrum above and below a certain bandpass, which in turn helps to increase the signal-to-noise ratio of important wavelengths. There are 2 main types of such filters: narrowband filters, which are usually used to study light from certain elements, like hydrogen or oxygen, or broadband filters, which is the kind that we used, which range from ultraviolet, visible, blue, red, and infrared.
We used astronomical images of the open cluster NGC 2194 provided by astronomer Tom Rutherford. We had 6 total images, each taken with one of 3 different filters: B for blue, V for visual or green, and R for red. And each image was taken with 2 different exposure times, one being 3 seconds and the other 120 seconds. And this was done in order to capture both the bright and the faint stars. The one that can be seen on the right is a 120-second exposure of V. These filters are also broadband, meaning that they collect light across a wide range of wavelengths, which makes them ideal for tasks like main sequence fitting. For our analysis, though, we mainly focused on the blue and the green filters, since they're sufficient for the color magnitude diagram that we needed. Next, we used a software tool called AstroImageJ. Again, we looked at the B and V filter images, specifically the 120-second exposures, to perform our photometry. First, we uploaded the images into the software, and then we identified the reference stars and their magnitudes based on previous data we've been given, and this can be seen in red. Then we selected our target stars, which can be seen in green, and this gave us their brightness, or magnitude, based on the number of photons that the software could detect. Then, all of this information was carefully recorded and organized in a spreadsheet for later analysis.
Photometry was one of the most essential and important parts of this project. To perform it, we used a software called AstroImageJ. This tool allowed us to analyze and extract data from our cluster, most importantly, helping us calculate the apparent magnitudes of various stars. By inputting the known magnitudes of our reference stars, as shown to the right, AstroImageJ was able to determine the magnitudes of surrounding stars using 2 filters, B and V. These filters isolate specific wavelengths of light, blue and green, respectively, by blocking all others, enabling the software to accurately count the number of photons received from each star in those bands. AstroImageJ was a careful process that took several tries to get clean results, but even despite that, it was a huge help.
Our initial step was to develop a consistent numbering system for stars within the open cluster. We used the galactic clusters NGC 2126 and NGC 2194 as a reference. We divided the cluster into rings and assigned each ring to a team member. Unlike Cuffey's study, which was limited to a small subset of the brightest stars, our modern data included 4 more stars, allowing for a complete analysis of all 816 stars in the cluster. This larger sample allowed us to estimate the cluster's age and distance more accurately than was possible in 1942. We classified stars using their color and brightness. The inner ring was a dense central cluster with a mix of F, G, K, and many M-type stars, which shows a range from yellow to red dwarfs, with temperatures roughly 2 to 7,000 Kelvin. The second and third rings included mainly A-type and F-type stars, as well as cooler K-type and G-type stars. We rarely recorded O-type and B-type stars. The fourth and fifth rings contained less stars and consisted of largely colder K-type and M-type stars. The histogram on the right displays that K-type stars were the most common within our cluster. Our HR diagram revealed the age of our cluster. We found out that most stars lie along the main sequence, confirming they are in the hydrogen fusing phase. A clear turnoff point near spectral type beta 8 indicates where higher mass stars are evolving off the main sequence. Comparing the turnoff with stellar models, we estimate the cluster's age to be approximately 30 million years old. The mix of F, G, K, and many M-type stars shows a varied stellar makeup, with cooler, lower mass stars concentrated in the inner regions.
Reddening. What is reddening? When light from star passes through interstellar dust and gets altered, the blue light coming from the direct object is strongly absorbed and scattered by the dust, essentially removing it from the light reaching us and making the object appear more redder than they are. How do we measure reddening? We can determine the degree of reddening by analyzing the color index B minus V of an object and comparing it to its true color index B minus V. Why does it matter? Reddening allows us to accurately determine the cluster age and distance. Finding age and distance, we estimate the turnoff to be roughly 0, 13.5.
Our turnoff of color index of 0 is closer to B-class star, meaning the approximate main sequence lifetime of the age of NGC 2194 is 30 million. Then, using the distance modulus equation to determine the distance of a cluster, we need to use the distance modulus equations in which the d is the distance in parsecs, m is in magnitude, m is the absolute magnitude, which is unknown, so we need to use a star that is known as a reference star, which will be our sun b minus v value of 0.65, v magnitude of 8.83. And using a similar star in a cluster with a corrected v value of 14.9894. Then we substitute the variables into the equation. We get 10 to the power of 14.9894 minus 4.83 plus 5 divided by 5. And we get the distance of the cluster approximately 1076.7 parsecs. Comparison. Since in 1942 there's a limited technology compared to modern technology access, we found that the differences are in the number of cluster stars. We number over 800 stars as part of a cluster, while Kuper numbered 120. Distance of a cluster. Kuper determined that they were 1,200 parsecs, while we determined it was around 1,100 parsecs. Kuper and our main sequence turnoff got similar spectral type stars, a B class. What we expect differently in Kuper's 1942 photometry 2 hours are the photometry accuracy, stars detected, estimated distance, and reddening.
The importance of our results within astronomy as a whole lie in refining stellar evolution models by allowing astronomers to determine whether predicted colors and brightnesses match our theoretical models based on the cluster age. This study can also help scientists better understand physical dynamics in gravitational bound systems such as NGC 2194, or calibrate luminosity measurements to allow for the determination of absolute magnitudes of other astronomical objects. Finally, we have laid out a rigorous pipeline that opens the door for examining the age and distance of other open clusters in the future. Throughout the NASA's research process, we enjoy learning how to operate industry-level astronomical software, such as Astronomy and Stellarium. We love collaborating with driven and motivated students who are interested and knowledgeable about astronomy, physics, and a wide variety of fields. We truly felt that we were conducting authentic and valuable space research and contributing to the future of science. We have learned so much in our short time together, and this is truly an unforgettable project that has taught us more than we could ever imagine. I would like to thank Dr. Olivia Kuper for her invaluable mentorship and advice throughout the entire research process. We would also like to thank Mr. Thomas Rutherford for data collection for our images of NGC 2194. We would like to thank Southeastern Association for Research in Astronomy for their use of the telescope, and the University of Texas at Austin Center for Space Research, the National Aeronautics and Space Administration, and the NASA STEM Enhancement in Earth Science Internship Program for bringing us together and allowing us to conduct this project. Thank you so much for your invaluable help and support.